are ready, or
Just, I mean, another minute or?
yeah, maybe it's just streaming always like
Everyone's
trying to
expecting?
keep.
Yeah. Okay, yeah, it's fine.
Yeah, let's wait. I'm just gonna say something. Okay, for those of you who are watching us online, we're gonna wait another maybe 5 minutes for people here who had to go very far away to get lunch. So not everyone is back, so we need to wait a little bit. So we'll probably start, in about like 5 minutes or so.
Okay. Okay. Were there any questions from the YouTube chat? Were there questions on the YouTube chat in the morning? Okay. Yeah.
I think we, sorry. Okay, welcome back everyone to this new session this afternoon, which is going to be about workshops. So we're going to start with a workshop by David Braun, and it's going to last about an hour, and then we'll have another workshop by Miller, and then we'll take a break for 30 minutes, and we'll have a final workshop with Celeste. And that's kind of the program for this afternoon, and maybe after that we can all go for a drink somewhere else. So yeah, again, like about an hour. You know, like I think time is slightly more flexible this afternoon than this morning. So you know, like I guess 3:10 or something like this. So yeah.
Or two. Okay. Thanks everyone for sticking around for the workshop. This is going to be pretty technical, but I want to work with everyone's comfort level. So I want you to interrupt with questions and try to make it more interactive, because if you don't, then I'm just going to walk through a lot of code, and it could be boring. So I'm trying to be receptive to how you're feeling about it, and we can move on to a lot of other topics. It can be a kind of open-ended discussion. So maybe I'll start there. Like, are there leftover questions from the morning session from anyone? Yeah.
Did I get it right? Wait.
Oh. If you say it out loud, I'll repeat the question into the mic too. I can just do that.
I think we need
yeah.
Otherwise, people in the streaming won't hear anything. So. It's good after lunch.
Yeah, thank you for the presentation once again. And did I understand right that you're working on a system that is able to figure out what signal path structure on the underlying signal generation could explain a certain signal?
Yeah.
That you give it as a target signal and reproduce it kind of?
Right, yeah, it's a pretty challenging problem, so I don't have a solution yet, but I'm working in that direction. The beginning part of the morning talk was talking about optimization and machine learning. So for a given DSP, how do we optimize the numbers that are used in that DSP? But then that latter portion of the talk, I was trying to say, how do we explore the space of all possible programs, all possible topologies of DSP? To decide that this parameter needs to be modulated by an LFO, and the thing that's driving the frequency of that LFO needs to be an envelope, and so on. So it's a very open-ended and large design space. It's basically the space of all designable programs, which is enormous. But we're trying to, first of all, restrict it to an audio DSL to say we're going to work with Faust, or more specifically, we're going to work with the Faust Box API. And then, moreover, we're trying to continue to clamp it down further and say we're focused on the design space of modular synthesizers. And now, for even narrower than the space of modular synthesizers, you might say, I only care about these specific modules, and I only care about, and so on and so on. And you keep restricting the design space, and that is an essential part of program synthesis, using domain expertise in order to restrict the search space and also traverse it more intelligently. Yeah. So on the topic, something that I brought up at the end of the talk was that paper that was the blind estimation of audio processor graph. So I think that using Faust, using the Faust libraries to improve that line of research and to do to have generative procedures for making these audio processor graphs, to get instruments involved too, and then also to have it be differentiable. That's a really, I think, promising line of research in the future.
So we could think of a future where you take a finished track from a DJ or something and you put it into a system which outputs like an Ableton Live file that you could open, and where you would have like the whole recreated track kind of.
Yeah. So, I mean, that brings me to this topic here, which is this GitHub repository that I'm showing you, which is called DAW Dreamer. So I started this in 20.
I don't want to take too much of your time with that, but.
No, I'm answering your question.
Okay, good. Thank you.
Yeah. So I think that this project DAW Dreamer is kind of the idea that one of my main goals in however many years it's going to take me to do it is to work on something like that, as potentially nefarious as that sounds, to have a song and to deconstruct it, or as another researcher, Cristani, who has called it, to decompile music, to take an existing track and to decompile it into everything that's going on, the separate tracks, what instruments and effects are used on each track, and what are the parameters of those things, and to just do full analysis and reconstruction of music. So yeah, I think that I think of the DAW itself as a kind of reinforcement learning environment in the same way that Atari and Go are video games. I mean, you don't necessarily have to use reinforcement learning, but to just think about DAW as an environment in which agents can take actions and listen to the results and have this crazy feedback loop, I think that that's just a kind of pipe dream, but that's why it's called DAW Dreamer as a project. Yeah.
Thank you.
Yeah.
Like we're just thinking about it during lunch, and like I was just wondering if one would have something like a synthesizer 808 or something, and like how difficult it would be to like just play something and turn all the knobs and do all these things, and then recreate all the action or the user interactions that happened only on this one instrument.
I'm sorry, I didn't understand, I think.
Like if you have a synthesizer, like a physical synthesizer, like an 808 or something, there are a lot of like simulations of that also. Like if you just have like someone play with that thing, do you think it would be easy or a good step towards this direction to recreate all the user interactions with the instrument just from the file? Because then you can like simulate everything, and you have like a very limited testing space basically, because it all comes only from one instrument, and you know all the interaction possibilities.
Yeah.
But I think this in my imagination, this could be a very nice step to also do it like instrument specific basically. But do you think this could work? Or?
Yeah, I think that brings to mind something else going on in this AI space, which is using kind of version control, as in software source code development, to inform how code can be improved over time. And so you have people scraping GitHub or looking at vast amounts of Git trees and the log records to the files, and they look at the git diff message and they say, what this git diff does or achieves is what is in the message. So they are coming up with these machine learning models that can take a message and predict the code change that was necessary to do something. And so the same thing is possible with synthesizers. If you have a human with all of our prior knowledge about what it means to interact with knobs and to explore what a synthesizer is as an instrument, you can have a record of the decisions that they make. And that would be like behavior cloning in the realm of reinforcement learning, to teach an agent to mimic what a human does to explore a synthesizer. So that's definitely something that I think people are looking into. I think that as of now, there still aren't a ton of reinforcement learning synthesizer projects, but it could happen, and there could be a big new wave of people doing it that way, I think.
Thank you.
Okay, so that's great. Please interrupt me with more questions. I enjoyed that very much. So we are looking at this GitHub repository called DAW Dreamer, and I want to show you, so if you have a laptop, please follow along, and because we're eventually going to be doing a Google Colab where you're going to run stuff in the web browser. So get to this page, github.com/dbron/DawDreamer, and I'll show you just a quick basic example of DAW Dreamer. So we can import DAW Dreamer as DAW, and now we import SciPy. You're not actually running this code. I'm just telling you about it out loud right now. So we create a render engine, and a render engine can load a graph of processors. We give it a sample rate, and we give it a block size. So here we create our first processor, and we can have unlimited FAUST processors. We can also have plugins. So you can load a VST plugin, and you can load, those are the two most important ones, but you can also use simple processors for changing to mix the loudness of multiple inputs. So let's focus on just the FAUST processor now. So we can specify our DSP code here as just a plain string, or we could load it from a file. And here we create an example called mySign. We declare a slider, and we declare a volume. And then we use the basics library for dB decibels to linear scale. So we have a frequency, and that goes into our oscillator. We multiply by a gain, and it's split out into stereo. Now, if I do get parameters description, then we're going to get a list of, it's going to be a list of dictionaries where each dictionary is a parameter. So you would get information to know from your Faust processor that the possible parameters that you have to manipulate are named frequency and volume. Here we load the graph, and then we set the parameters. So here the value was 440, and we just set it to 440 again. And here the volume started out at 0 dB, but we change it to -6 dB. An interesting feature here is that this could be a NumPy array. So if you wanted to say, I want my volume to be a sine wave or to be a linear ramp, rather than passing a single number here, you would instead call set_automation instead of set parameter, and you would pass that NumPy array. So this is a programmatic way of kind of interacting with the DAW. You know, there's no GUI here. It's not nearly as nice as something like Ableton, Logic, Fruity Loops, whatever. But it's a programmatic way of building audio processor graphs and specifying the automation curves for those processor graphs. So even if you're not doing anything involving the machine learning frameworks that I'm going to show you later, this is just a relatively high-level way of scripting and batch processing audio. So you're not using a GPU to do anything clever here. You're not doing backprop. You can just do this to take MIDI files, take a database of MIDI files. Maybe you would augment your MIDI files in some way, like using Music 21 or some other library, and you can render vast amounts of audio. And then you use that for source separation or any other MIR, music information retrieval task. So I think that this, there is an existing library called Pedalboard from Spotify that is quite strong at using plugins. And you know, I commend them for that. I think that one of the strengths of DAW Dreamer relative to Pedalboard is that it supports Faust. So you can, under the hood, it's using LLVM, low-level virtual machine, in order to render the audio, and you can also scale that up in terms of using multiprocessing. So it's pretty strong in that regard, and we all love Faust, so that's why I'm glad that it supports Faust. So there's some other examples here. You know, this is showing how you can add a MIDI note. So you specify that you want the pitch to be 60 and a velocity of 100 for the note to start at 0 and for it to last 2 seconds. And I could have also said, I want to load a MIDI file. And then when you load a graph, this is a synth, and then the synth is going into an effect. The effect could be a plugin. So like you're specifying the effect path, and this is a DLL, like a VST, on your Windows operating system. And then you load the graph, and then you render audio. So yeah, I think it's a good scriptable way of making music. Any questions about this? Yeah.
What is the path for the
These are placeholders. You change this yourself based on the specific plugin on your computer that you want to use. So this could be a .vst file, or it could also be a .component file, like on macOS. .component is a plugin type. Yeah. Also, the BPM feature is interesting. So you can actually set the BPM, and now your plugins, which can be BPM dependent, will respond to that. And you can even set an automation of the BPM. So this could be really interesting for making a data set that you use for beat tracking, because you could take something that's very rigid in terms of its timing, but you could add subtle variation with a NumPy array specifying that I want the BPM to, you know, be roughly 120, but with some human timing where the drummer is imperfect, and it's ranging between like 119 and 121 with noise. Yeah. Yeah. What is it a typo or?
Yes. The second one.
Oh, thanks. Okay. Thanks. I'll fix that later. Yeah. Yeah. And then you'll be a contributor. Yeah. Okay. Any other questions? Yeah.
Does it allow you to do real-time stuff?
No. And that is something that pedal board can do. So that's definitely a strength of pedal boards. Yeah. There are plenty of issues. I'm not shy about that. You know, plenty of bugs, plenty of requests. Most of them are related to people saying this specific plugin doesn't work, and it's kind of out of my scope as like a researcher to support every plugin that exists in the world. But I've put in a reasonable amount of effort into supporting plugins. So if you want really good plugin support, go to pedalboard. Okay. So yeah.
How do VSTs and the Faust code connect? Do you
Yeah.
the VST as a Faust?
Right. So the main thing connecting all of this together is Juice. So you know, I give them. There are a lot of licenses involved here. Look at all of the licenses. Juice is involved. And then there's PyBind 11, libsample rate, and rubber band library. This is what does the pitch warping and time stretching, and Steinberg VST 2 and 3, and Faust. So, but Juice has this class called audio processor graph that they've been working on for a very long time, and that is what is going on. When you say load graph, this is implementing this thing here, synth, is a subclass of an audio processor in Juice terms, and we are calling load graph, and so we're really interacting with the Juice API via Python bindings to dynamically build this graph. And what's interesting is that this works even when your plugins have non-stereo inputs. So you could have a plugin that needs 4 inputs, you know, like a sideband compressor where you have your main, but you have your auxiliary input. And so here, suppose effect expected 4 total channels, 2 stereo inputs. Rather than putting synth get name here, I would actually do get name, comma, and then I would say auxiliary input dot get name. And this is just returning a string. So dot get name here is just returning the same synth argument that I passed here. So this text synth is what shows up here. So yeah, it's a very generic audio processor graph from Juice. Yeah.
And in terms of like API, the sync and the engine responds to the same function as the audio processor in Juice.
Yeah.
Like I see, they are the underscore, but they are like the same. They get new input channels and get new output channels.
Yeah.
They are the same of the audio processor.
Yeah, I mean, roughly, if you look at what I've done via the Python bindings, it's kind of just calling the method that exists on the Juice object. Cool. Seems like you're a Juice user, so that's good. Okay, anything else? Okay, great. So next topic is, let's go to the examples. So we're at Daydreamer. Now we're going to go to examples. And there are several notebooks here that I can talk about today, and I'll kind of adjust it, the tempo. So the first one that's highest priority to talk about is Faust to Jax. The second one is the Box API, and this is kind of related to that program synthesis that was the second half of my morning talk. And then there's also Faust to QDAX. QDAX is a quality diversity algorithm for discovering diverse solutions to a problem. And this is that parametric equalizer situation that I mentioned, where you have a parametric equalizer with 10 unknown variables, and we want to use this algorithm in order to figure out what those numbers were. There are some other examples here that are cool. DJ mixing does automatic DJ transitions, where I can have a song at this tempo, and I can have a different song at a different tempo, and I use Faust in order to, and I use the rubber band library to do pitch, not pitch shifting, time warping, so that even as the tempo changes, I'm smoothly transitioning between the songs. This could be really interesting for making a data set of DJ transitions, or to analyze how other DJs are doing stuff where they're using a low-pass filter and changing the cutoff and so on to transition between songs. There's also a mashup generator, and there are examples for using all of the cores on your CPU to render VST one-shots, but VSTs can use up quite a bit of RAM, so you may not necessarily get away with using all of the cores of your computer. Okay, so let's first go into the Faust to Jax notebook. So I'm clicking here, and then I click on the notebook file. Here we're still on the GitHub page, but now I'm going to click on Open in Colab. So this takes me to Google Colab. So, there's going to be a lot of technical information here. I would say revisit this notebook as much as you want and email me with questions or file an issue on GitHub, stuff like that, so that we can improve it together. This is just an overview that resembles what I did in the morning, what I'm saying here. So we're going to talk about that simple cutoff example where it's static, and then we're going to talk about the automation example where we learn the automation curve. Then we're going to talk about the differentiable subtractive synth, which is a really simple example. And then we'll do the polyphonic wavetable synthesizer, which was much more complicated, but much cooler, I think. So just to show you some other information about Colab, you should go to runtime at the top, and you should go to change runtime type, and you should make sure that you're on CPU. The reason for this is that a CPU at its clock speed is faster than a GPU. So if you care about just getting one item as one example of audio, you're going to get faster results by using the CPU. But if you're doing a large computation where you are kind of using machine learning to do optimization, then you might want to use the GPU because the GPU is doing everything in parallel, which means that if I want 100 items, it could be exactly the same speed as getting 200 items and 400 items and so on. It's just a limit of what your graphics card's memory is. And I've confirmed that in my experiments, but just because we aren't doing a large batch size, we only care about using the CPU in this Google Colab. So that's why you should make sure that you did runtime typing and you changed it to CPU. Also, if you were to do GPU, then you would want to do this code here where I would change CPU to GPU, and then you could use the power of your GPU. Also, installing GPU on Windows is the most difficult thing, but I've done it before. So to use JAX with a GPU on Windows, you have to use WSL. So, and I use an educational license of PyCharm, and PyCharm works really well with WSL. So that would be my recommended approach to Windows, GPU, and JAX. Yeah.
David, can you, because it turns out my collab is in French, so I'm not sure of where I should, the runtime, which is execution, which one? Okay, this one. Okay, no, I got it. And so the recommendation is we stay CPU, right?
Yeah, use CPU. Okay, so now what you need to know is that this, this is text, and if I click on it, if I double click on it, then I get Markdown, because it's actually Markdown. And I get a live preview on the right here. What's this? This is changing the live preview. So yeah, I'll keep that there. And I have my text on the inside, and I'll hold Shift key, and then I'll press Enter, and that's going to collapse it and bake it down into a text rendering again. So now this is just Markdown, so we're not executing it. And now the very first thing is we do install and setup. So I just have my mouse inside here, and I could either do Shift return, and that runs it, or I could click the play button on the left. So I did Shift return, and now it's installing some stuff, and you can see that it's executing over here on the left. Okay, it's going. So we are installing NumPy and SciPy, Librosa for reading audio files, and then these are all JAX libraries that are related to each other. Okay, so now the next step is to do this one. So here I'm doing the play button to demonstrate this, and it's installing DAW Dreamer. Any issues so far? Okay, yeah.
It's working on the cloud or on the...
It runs in the cloud. Yeah, this is not installing to your local file system.
So and it's free, you can use the CPU, but maybe if you use
I think the GPU is also free, but you aren't getting a great GPU. And the other thing is that you will time out. So you can't just run this notebook for 24 hours. It's going to cap your time limit unless you pay for it. And it's $10 a month to pay for the faster one. OK, so now we're importing the libraries. I grouped things together. So these are all JAX related, and then these are all Flax related. Flax is kind of like, you could think of Flax as PyTorch Lightning in a sense for people who've used PyTorch Lightning before. OK, so now we're executing this one, and I'm just going to. You don't have to mouse click every time you do this. You can just hit Shift, Return, Enter, and you'll keep going down. So here we got down to the Faust example, which I'm skipping because I'm assuming everyone knows enough Faust. And now we are going to proceed with the following Faust code. So this is just our plain text string of Faust. And we want to convert it into a box, first of all. And we're going to go from Faust code to box, and then from box into JAX code. But before I show you the JAX code, I'm going to show you the C++ code. Now, if you use Faust on the command line, it should be familiar to you where you just type Faust and then mysource.dsp, and that's actually going to return C++ by default, I think. Maybe you have to say -lang CPP. But this is an equivalent Python way of getting that same text information. So we say box from DSP with our Faust code, then we get a box, and we can assert that the box's inputs and outputs both equal 1. You can see that this is a cutoff with 1 input and 1 output. And then we get our CPU code. We could do this alternatively, where instead of using Faust context, we have to create a lib context, and then we have to destroy a lib context. So anytime you use boxes or signals, it has to be in this safe sandbox zone using Faust context or lib context. So that's a kind of gotcha, but it's not hard to do. I typically have a main function, and then there's the syntax where you do if __name __ equals main, and then you say execute main, but then I just say with Faust context execute main. So anyway, that's one way to do it. So we got our C++ code, and then we print it. And now this is the C++ code of our low-pass filter with a cutoff. And I'm going to scroll down, and we see a compute function. And the compute function has a number of samples to generate. And we have a for loop with that number of samples. And here we have the main one pole logic. Outside of that, these are where the UI parameters are used, and that's why they're given this name slow, because they're only updated once per block size. OK, so that was C++. Now let's look at the JAX code. So I executed the next box, or the next code section that looks like this one. And now we have a full Faust or JAX example. So it starts with the Faust license, and then it imports some things that are JAX related. And now we get class myDSP. And so the class myDSP is named that because we declared it here, module name myDSP. And and also an important thing of using the box to source function was that we specified an architecture file. So I want to take a poll, please be honest. Who has used an architecture file before in Faust? OK, not a lot, so I want to talk about it more. So when you convert Faust code into an architecture file, you are targeting a specific kind of application. So sometimes you want to support various device drivers and codecs and things that like to work with Jack or various things with Linux. And so you're telling the compiler to use more specific things when you're doing a code conversion process. So in C++, there are many variations of this, many different architecture files to use. JAX right now only has one architecture file, so that's minimal.py. But minimal.py, maybe it can be expanded in the future. Maybe talk to me one-on-one about how we can make variations of architecture files. So It's kind of a template that is being filled in when we're doing our Faust to JAX conversion. Yeah.
So I saw that you still have the GRAM copyright, but
Yeah.
you wrote this architecture file, so there's no copyright for that.
Okay.
Really?
Oh, you mean like Graham doesn't own it, I own it?
Yes, you can write every architecture file that you want.
Yeah.
So the architecture file, the copyright is the copyright of the one who wrote the architecture file.
Okay.
So since you wrote it, you can put your own copyright.
Okay, that's good to know. Sure.
So basically, the copyright system in Faust is what's going in is what goes out.
Yeah. So I could have put David Braun, give me $1 million if you use this code here, but I didn't because I like you. Okay. Yeah, better decision. So now this is the file, and you could have gotten the same Python source code on the command line. I'm emphasizing that, and it would have been spit out as converted.py or whatever you specify as the argument -o, some Python name. But here we have it as just plain text in this ecosystem. So I'm scrolling down to the most important function, which is tick. So tick is basically equivalent to what the compute function was in C++. So it's important to kind of study this code sometimes, like the hardcore Faust developers who turn their Faust code into C++ code, they're often looking at that C++ code and doing a gut check on whether it looks fishy, whether it looks like it's doing something dangerous or slow, something that could be optimized further. So here we are looking at the tick function to know what is going on in our JAX code. There are some other things in here that I'm going to skip for now, but these mostly relate to loading sound files. So there's the sound file primitive in Faust when you want to load a WAV file and play it back as a read-write table and so on. And so you can override this method, this load sound file, and you can if you were to, you'd have to modify the architecture file. That's what this purpose is. So if you wanted to have a custom way of if you refer to a sound file, but you want to replace it with some magic numbers that don't actually exist in a WAV file, but can just be generated on the spot, then you would override load sound file and so on. And there are other methods in here that come from the architecture file if you look at that yourself. So this is how sliders get created, and this is how entries get created, and so on. And there's near final thing I'll say about this is that there is a test function. So if you were to convert your Faust code into JAX and run it on the command line, by default, it would be using this test function. So that's a good thing. And we use that for confirming that the outputs of the JAX conversion process actually match what C++ does. So you can rest assured that this Faust to JAX conversion process is actually robust because we've compared it to exactly what the C++ code does numerically and made sure that with floating point precision, it's actually generating the same thing that C++ does. So yeah, so this is our code that got generated, and this is everything that I talked about earlier, where you could have named it myjaxcode.py, and you could just run Python myjaxcode.py --help to understand how to use it on the command line. And if your file that you generated on the command line was called myjaxcode.py, then in some other Python file, you could say, from myjaxcode, import myDSP, because our class was named DSP. And then you instantiate myDSP, and then you use that as a trainable neural network in JAX. This is very similar to what the other popular PyTorch libraries are doing. They're making individual files where each file is a DSP, a differentiable DSP class. Like they have a class that has a compressor module and a stereo effect module and so on. But all of those modules were coded by hand and are kind of prone to error, I believe, or maybe not that efficient. But if we use the Faust to JAX conversion process, then we can rely on all of the tested Faust code in the Faust libraries, and you don't have to bother manually differentiating code. Yeah.
So you say you make a neural network from the program, the
Yeah.
Is it the cutoff?
Yeah.
Or is it not code?
It depends what existed in this file here. So if Faust_code.dsp had an H slider in it, then this myDSP object here would have a parameter in it, and you don't have to think about that at all. Does that make sense?
I'm not sure I get what are the parameters?
Yeah, okay, I'll show you that. So if we look at this is the auto-generated Python code. So the important thing here is build user interface. So this mimics what is done in C++. So
So the parameter is the user interface.
well, let's look at this method, build user interface. You could see any number of lines here for every parameter that existed in your Faust code. So one parameter was named HF for float, H slider for horizontal slider, and then it's given the unique identifier 0. And we don't have to think about that. We didn't name that ourselves because it knows that it's named cutoff. But to give it just a more like unique name, it's given H slider because that's what the convention is in the architecture files. So you'd end up with any number of objects here, and each one calls add slider. And if you want to customize how add slider as a function works, then you do that in your architecture file. Okay, so I think I talked about this, and now this is some of the trickiest stuff in this entire notebook is understanding what is going on in this section. So I think that you really have to be motivated to learn about JAX to learn some of this stuff because it's really confusing. VMAP is what takes a single item and it turns it, I think it vertically maps it into a batch. So you write your code and you just, suppose you wanted to have multiple things of that function executed in parallel, VMAP is what helps you achieve that. So when we create the DSP class, I left it by default as a non-VMAPed class because I wanted to have the user VMAP it as an optional thing. So that's why it became necessary here. But definitely email me something or check out the documentation on VMAP that I linked to here. Like open that up on another tab and come back to it later because it's very important. It's the essential thing about JAX and VMAP and Flax and so on is this feature. VMAP is also implemented in PyTorch. It's the same idea. Okay, so back to the notebook. So I execute this item, and then the next thing is I'm going to execute this block, which is actually that one doesn't get executed. But you should read about how pseudo-random number generators work in JAX a bit, so bookmark that and come back to it later. And now we're going to do inference. So we have our DSP class, which we created as, we created a DSP class here. It's called model batch. Our function returned it, and so now we have hidden model. And then hidden model is what we use down here. So hidden model we initialize, and we give it the noise inputs, and these are full spectrum white noise. And then we get parameters, and now we actually pass our parameters to our JIT. JIT is just-in-time optimized function, and then we get audio. So what we're demonstrating here is that the first input is going to be the very loud white noise, and then the second one that I'm going to show here is the result of it being passed through our model, which is going to be the low-pass filtered white noise. So I'm going to play this at a low volume and see what comes out. Okay. It's only coming out of my computer. Maybe I'll fix that later. But yeah. Okay, so the next thing is about path names. And this is to emphasize that when I printed out the parameters, there are two different kinds of parameters. One is normalized and one is unnormalized. We only have one parameter here. It's the cutoff parameter. The cutoff parameter was 440. And so with floating point, for some reason, it's coming out to this thing that's close to 440, but not exact. And this is the unnormalized parameter. But the normalized parameter is remapped from its input range of like 20 to 20,000, which is what we declared in our Faust code. And we take that range 20 to 20,000 and we remap it to -1 to 1. And the reason we do this is because it solves an important issue of machine learning, which is known as conditioning. So the conditioning number, it has to do with when you have a valley, and I don't have a hand reference for myself, I think, but if you have two parameters, and you're optimizing two parameters, it's kind of like a valley. And if the valley is very elliptical, then when you follow the gradient, you can do a lot of zigzagging down to reach the bottom of the valley. But if your loss landscape is very circular, then that fixes what's known as the conditioning number, and you're going to have more of a direct path to the center of the valley and arrive at the global minima. So that's why this normalization strategy was necessary. So kind of behind the scenes, the numbers get normalized, but then we have this other procedure that presents them to you, the user, to translate into the human readable range, which is hertz, where it's 20 to 20,000, which is what you assigned as the range of your slider. So here I've kind of just talked through this information that was here, so we can keep moving on. I think also this link is kind of interesting because this is what is doing it under the hood. It's called the SO function, and so we SO our intermediate variables where the values that are being SO'd are the remapped values that are in the human range that we want, that are like the 20 to 20,000 number, not the -1 to 1 number. So bookmark that and come back to it. Okay, any questions so far? Okay, sorry that it's pretty technical. So here, the next thing is maybe more exciting because we're actually going to be training it. So we are going to suppose that our initial cutoff is 10,000. You can actually control this with a slider over here. And you can set the batch size and the learning rate and the momentum. This is just a very naive, I forget the exact optimizer that we're doing, SGD. SGD is the most boring, ordinary optimizer. And so the results aren't perfect, actually. But I think that if you looked at the optax library and picked a different optimizer, then you could get more stable results as the loss approaches 0. So we are going to create all of this kind of boilerplate code that is kind of ugly, and we create a train step. So the train step, importantly, has @jax.jit. So this is a decorator function in JAX. So it modifies, it wraps or decorates this function. And it's important because this does just-in-time compilation of the JAX code, which means that it can be slow to compute the first time that you run it, but then on subsequent runs, it would be very, very fast because it's compiled for your specific CPU architecture or GPU architecture, et cetera. So here we have a progress bar, which is the number of training steps that we want to do. And then we have this loop here. So we are generating a new noise on this line, and we are generating a new ground truth filtered noise. And what our training step receives is our input and our output, but we are trying to figure out what was the cutoff parameter that was used to turn X into Y. So it's like here, JIT hidden, it actually had a value of 440, and that's why it was able to do the low pass. But here, when we call it train step, it's on a different model. That different model was initialized with a cutoff of 10,000, but over time with gradient descent, it's being optimized to be a value of 440. Now, the line down here, where I call JIT train inference, it's actually returning two objects. The first one is the audio, but the second one is the human readable range of the output parameters. So going back to the discussion of normalized versus unnormalized parameters, these are the unnormalized parameters, and this is related to the SO function. So when we called SO, the architecture file took care of this for us, but SO was doing the work of making sure that mod vars contains our unnormalized parameters here. So let's run all of this, and we get a progress bar. You saw that the cutoff was starting at 10,000, and it's falling over time to 440. Should get there pretty quickly. Also, when I was running this on my Windows computer with a nice Intel CPU on it, this runs like 4 times faster, or maybe even 10 times faster than the CPU on Google Colab. So we ended up with the cutoff value of 440. Now let's plot it in the next box. So we're showing 2 graphs here. This is just the loss over time, the evaluation loss, and we plot it on 2 scales. So here we saw that the loss starts at 0.3 and it basically falls to 0. But on a log scale, it's kind of falling to 10 to the -4th and 10 to the -5th, and it's kind of getting stuck there. And that is just an issue where it's kind of zigzagging infinitely because we're not taking our step size, our learning rate step size. It's not falling to 0. So that's why you kind of get this zigzagging around 0. Yeah?
I have exactly the same curve. Why is it so reproducible?
Yeah, because we all probably have the same seed function. So, I mean, it's very high up here, but there's this seed value. I don't know where the first, yeah, here, I called it here. So if I were to change this magic number to something else, then we'd get different results. Yeah. You also, I mean, in JAX, you also have to take care that there's this interesting thing where whenever you're generating random numbers, you're always passing a key, but more specifically a subkey, because you take your key and you split it, and now everything that's downstream of that subkey is actually independent of the other key that remained. So it's this kind of a hierarchical key generation process that allows you to have, it's still deterministic, which is what you want because it's all based on a seed value, but it also just allows this very wide branching effect where it scales very well with random numbers. Okay, so we've generated our loss and it converged to 440. And as I mentioned, we were just using SGD, which is very boring, but there are more interesting optimizers in the Optax library. Okay, next thing that we're going to plot is the loss landscape. This is really important for debugging. So if your system only had 1 parameter, then you could plot this loss landscape. But if your system has 100 parameters, you might want to hold all of the parameters constant except for just 1, and then plot this loss landscape curve to get an impression of how chaotic the loss landscape is. Because that could show that machine learning, or at least by following gradients, could be a kind of hopeless endeavor. And you may want to rely on other methods like quality diversity or genetic algorithms or all the other opportunities for machine learning that don't involve gradients. Okay. So here we're going to do speed benchmarking on this next box. And what I want to talk about here is that we are comparing it against SciPy as our relative competitor. JAX is doing the same code that we defined earlier, which is a low-pass filter. But we're doing the same low-pass filter with the SciPy function L-filter. So I'm highlighting that here. L-filter is, does it stand for LTI? Or this is good trivia. It's an IIR filter. It takes the B and A coefficients that you can get from a Butterworth low-pass. And so I believe that this Butterworth low-pass is a 1. You can see I specify 1. And that's why it's a 1-pole filter, and that's equivalent to the Faust code that we specified earlier when I did fi.lowpass with a cutoff. So we're comparing JAX against SciPy, and we see that it's 2.57 milliseconds versus 7.14 milliseconds versus SciPy. So that's great, right? And what's even cooler is that SciPy, we gave it B and A coefficients, but actually we did a batch size of 100. So you could actually give different B and A coefficients to every item in our JAX filter. You know, we did just this Butterworth low-pass filter, but it could have had more arbitrary components, but the same number of components because it's a first-order filter, and it would just be like varying the cutoff. That's what, if you change your cutoff value, then you get different slightly different B&A values, but they're the same dimension size. And we would get different results in every item in our batch, but SciPy is only capable, to my knowledge, of having the same B&A coefficients used in every item in the batch. So JAX is faster than SciPy, but unfortunately, let's change this duration seconds to 0.5. And we'll see that on Google Colab, they become more comparable. Like they're roughly the same now, so the savings went away. But in my experience using a desktop computer, even when the duration is 0.5 seconds, JAX is still faster than SciPy. So I suspect that something is going wrong here in terms of the CPUs that are used in Google Colab, and it would be, you can get better performance relative to SciPy when you're using a Windows and, yeah, a desktop computer. Okay, so now we're going to move on to the cooler example from the morning talk, which was optimizing the cutoff automation. So cutoff is no longer a static parameter. It's actually a parameter that we change over time. So we define our code here. And here we are using the widget modulation, this relatively new feature in Faust, where we have our fx, but we are doing this arrow sign operator in Faust, and we are accessing the cutoff slider that exists, and we are doing this replace. But replace could have been something else. I think by default, it is an addition operator. So by default, it's probably, what? Multiplication, sorry. By default, it's this, but we are instead doing replace. So this is saying replace, cut the slider that exists inside, and then insert a wire so that you get a new continuous audio rate cutoff signal. So that is our new modified Faust code, and we convert it into JAX code, and now from our JAX code we have our filter. So this is just a single filter. It's not meant to be a batch yet. It's just meant to process a single item and it has two inputs. It needs the filter cutoff. It needs a tensor in machine learning terms, a tensor where it has two channels. The first channel is the cutoff, and the second channel is the signal to be filtered. So we create our filter model class, and then we create a hidden model. And the hidden model is what we're going to use for we're going to give a ground truth automation, animation of our cutoff, and that's what the hidden model is. And now we create automation model. So this is kind of similar to what's going on in an architecture file, but we've coded our model ourselves. And I think that this looks maybe ugly to some extent, but I think it's definitely no worse than what exists in other libraries. I mean, sometimes you kind of have to get down to business and code a neural network architecture yourself. And this is just an example of that. So call here, __ call, is similar in other machine learning libraries to the forward method in PyTorch, or the call method in TensorFlow and so on. You always kind of have to implement something like this. So what is going on is we are creating a cutoff parameter, and we are going to, this cutoff parameter is a time series, and it's a time series of a length that we are specifying, but this time series represents our automation that we are going to optimize. So we could specify it to be the same number of samples as our audio rate, but that would be kind of expensive because it would be equal in size to the length of the audio. So if you were processing 1 second of audio, then this might be a tensor, a learnable tensor with 44,100 numbers inside it. But instead, you can work at it at a smaller cutoff array. So self.automation samples, this could be a smaller number. And then what we do is we clamp it to a safe range, and we remap it. This is what I mentioned earlier about why we used normalized parameters, because this is safer for machine learning. And then we remap it to our desired range of 20 to 20,000. And that that makes the filter stable. And now we do interpolation, where we take our time series, which might be small, it might only be 40 numbers, but we stretch it over our desired audio length. So T here is the input that has been passed to the length of the audio that we want to generate, which coincidentally is, of course, the length of the audio that has been passed to it. So then we do something where we have to expand the dimensions, and this increases the dimension size, and we concatenate our cutoff to our signal to be filtered. And so this is now a tensor with 2 channels on it, and we pass this tensor, x, into our filter model. So we create our filter model, and we give it a sample rate, and now we call filter model on x, and we give it the number of samples to produce, and this is our audio. So let's look at how we created it. So we said automation model, and we specify a number of automation samples. But what is automation samples? It's the length of the audio that we're generating, t. So that would be like 44,100 for 1 second of audio. But we've downsampled it according to this number here. So I'm going to first downsample this a lot to make it very apparent what is going on. So I'm actually going to do 1,000. And now I'm going to run this. Okay, so it didn't train yet, and now I have to keep doing the next box. And here it pointed out that our cutoff param shape was 44. So our cutoff animation that we're learning is just 44 numbers, but we're stretching it over, I think, 1 second of audio. And I'll keep executing the boxes, or the code snippets. Okay, so here we're doing the training, and it's training very quickly. It descended, but you can see that it's getting stuck at 0.01, and that's because our model doesn't have enough learning capacity to smoothly match the ground truth. So it trained, and I'll execute this one. And now we are going to get a plot, I think. So here, we got an animation, and it trained very quickly. But now if I pause, you can see here that this is not matching that peak very well, because our model's learning capacity was only 44 numbers for an entire second worth of audio. But let's go back and execute this one more time. So I'm going to automation downsample, and I'm changing this to 10. So that's 4,000 numbers, roughly. So it's more expensive to train. And I'm just doing shift return to execute the following code snippets. And it's training. Oh, you know, it's I think actually because I changed the number of parameters, the learning rate needed to change. So this is some live coding. So here, let's take our learning rate, and we will actually, I don't know, do it live. I'm going to change the learning rate and see what happens. Okay, it didn't work. Maybe I needed to go the other direction. What should I do? I'll do one more attempt, and then I'll just change I won't do such a large parameter. Oh, okay, this, not quite working. Let's see what it looks like when it's done rendering. Okay. Didn't quite work. So I'm going to go back to our downsample, and I'm going to change this to 100. Execute, execute, and I'm going to change this back to -1, I think. Okay, so this is going to succeed. So yeah, because those are the numbers that I chose for the morning talk. But you can see upon visual inspection that it's matching the ground truth in blue much better. And I'll take a risk. Let's do something more exciting even. I will go to the ground truth, which is this blue curve, and I'm going to modify it. So let's find where that was. Here it is. So this is the frequency that I was using for that ground truth. So let's change this to double. So the number of cycles that you see here is going to double. And we'll see what happens. Okay, it's working. So yeah, the ground truth that we chose is totally arbitrary. It could be any array that you come up with. Now let's plot it. And there you have it. Even though the cutoff is much more chaotic in a sense, with the model's learning capacity, was able to recover it. And it's not looking at the blue line. It has no awareness that the blue line exists, because it's only looking at input audio and output audio, and the only thing it can change is this cutoff parameter automation over time, and yet it's able to recover the hidden latent signal of this cutoff animation to get the loss down to 0. So I think that's cool. Any questions? Yeah.
How do you explain the fact that it converges in this fashion, like the shape of the conversion, of the prediction? Is there anything to take from the?
I mean, it's cool. It kind of feels like it almost feels physical, because it's like when you have a string and you just move you move the ends of the string upward, but it's kind of sagging in the middle. That's kind of what's going on here. I think there's no normalization going on here. So, for instance, when we coded our model here, we created this parameter. You could add an additional constraint in here where every gradient update, you have your cutoff parameter, but you could blur it. So every update, you would do a gradient update, but then each sample in your automation time series could be a convolution, a blur of its neighbors. And that would bring some stability, so that you, for instance, you wouldn't have a totally chaotic prediction where the cutoffs diverge. And I think that when I showed that example where I think I downsampled, or I did I set the downsample to only 10. So it was 4,000 numbers, and I think that it failed because it diverged in a bad sense. And so as you, if you want even more resolution in your cutoff animation that you're inferring, you probably need to add some kind of regularizer. Is that making sense?
I was also asking myself why do peaks and dips converge slower than the but I think it's pretty hard because architecture is so complex.
No, I can explain that. So at some point in here, the cutoff is initialized. Sorry, where can I find this code? Oh, okay, so look at this. Our automation model, when we declared cutoff, we initialized it with a constant value of 0, and this is up to us. I could have changed this 0 to, let's do it one more time. I'm going to change it to -0.9, in between -1 and 1. So let's look at our plot. So here, the orange line is starting in the middle, and I mean, roughly they converge at the same time. But let's run it one more time. And we're going to see that the orange line is going to start lower. And ultimately, I hope it succeeds. But I think that the bottom is going to be solved before the top portion is solved. Cool. It's working. So if you have some domain, knowledge about like an initial guess of what that parameter should be, the bad thing is you have to remap it into this -1 to 1 range because that's the correct machine learning technique to like make it more stable, I think. But you just when you're coding this yourself, you do that. But this looks like a pain, but I think it's just as good as anything else, any other library for this purpose, and yet we're still taking advantage of our low-pass filters and our oscillators and all the cool stuff that exists in the Faust libraries. Okay. Yeah.
You knew very quickly when it was failing, and I saw the error jump straight down to 0.01 before it and just hovered there. It was only like, a tenth of a second like that. Why is it behaving like that? And can you use that somehow to automatically know that it's failing?
Yeah, I mean, early stopping, for example, is like a solution to that. Like if it reaches a value of 0, that may be the wrong answer. It may just be a case of overfitting, and you may want to not use it. But sometimes it's actually like the right thing, and there might be something else that's causing it to explode. So I don't know the answer really.
The funny thing is it always failed a lot faster than it succeeded. When it succeeded, it was very, very slow.
Yeah.
It always just jumped straight to fail.
Yeah. Yeah. Worth exploring more. Okay, any more on this? Yeah.
Can you take advantage of Faust also to generate the automation signal, for example, and the
Yeah.
input signal?
Yeah, for sure. So maybe Daydreamer is a handy way of doing that. Yeah. I mean, if you coded the Faust yourself, then you could have a JAX thing that produces the audio that is the hidden cutoff. And this is kind of what I'll get to later. So how much time do I have again?
I think you're already past.
Oh. Oh yeah, time was flying by. Okay.
Yeah, sorry. It's just that we need to leave the room by 6 this evening, and otherwise we're going to be like in big trouble. So.
Yeah. Okay.
So I just, and there are 2 more workshops. I mean, this is like super, super interesting, and I'm sure like everyone would love to continue, but I think we, unfortunately, it's Saturday, and time is kind of limited, so.
Okay, very good. Well, just, do the collab on your own and make GitHub issues, email me, etc. Happy to help out. Thanks.
Cool. Thank you, David.
No, all good. Yeah.
This is, could watch this for like 3 hours, but like, so. Do you want your computer?
Yeah.
Yeah. I can.
Oh, okay, thanks. I don't know if I need it or not.
David, is this yours?
Yeah.
I can give it back to you. Yeah. It's like. Okay. Yeah. Do you need audio out of the computer?
I'm going to just hold this thing up to there.
Yeah, I think that's. I'll
To hell with
give
it.
you the
Okay.
the
Oh, that
microphone,
works too.
I think that's.
Okay. Yeah. All right. Awesome. Okay, I'm going to be boring, so you're going to be happy that we spent all that time on the interesting part of today.
What I want to do is, for those of you who want to do it, get you to where you can download the machine learning example of this morning and run it under pure data. And if you don't want to do that, like if you hate pure data or something else, you can just follow along, or you can go have a sandwich or something. And I don't think this is going to take very long. The difficult part is going to be getting to where you can run pure data, and the easy part is going to be grabbing the package. And what I'm going to do to get it started is show you where the package is, so that those of you who've got pure data running can get there first. Hello, what was that? Okay, so I don't know why I have to do this, but I think normal people, if they type in msp.ucsd.edu, get the HTTPS thing. It doesn't matter, except this one you can actually believe that it's correct. And then what was it called? Fan PAW 23.zip. Oh, quite possibly, but I don't know how. Let's see. Actually, let me just copy this and throw it in a text editor or something like that. Yeah. I don't know how to do normal things like this. I just do bizarre stuff. How do you change the font size on this puppy? Oh, God. Is there a... Oh, I know. Let's do this. Copy, paste. And now I think I have probably a GUI thing that will work here. Yeah. Don't do anything the way I do it. Hit it, and it didn't do it. Oh, okay, right. There you go. Yeah, maybe. There. So here is, except with either this or with an S, as you prefer. And this will be a zip file that contains, let's see, well, it'll contain a few examples, including the ones that I was looking at this morning. And it also contains a compiled external object for PD that will work on probably Mac Intel and probably not Mac M1. I can't remember now if I have it for let's find out. Okay. Patch machine learning. Hello. Okay, I'm just realizing as I'm saying this, I only have the x86 version of this for Macintosh, so those of you who are wanting to run on a Macintosh will want to run PD as an x86-64 program, which I have just learned to do. and if any of you is trying to do this, I will try to guess how you would do it from this machine and probably fail, but I know it's possible. The trouble with PD is that it is it's two programs, and when you just click on the thing like people do on Macintosh, you get the GUI, which is not PD, and then when PD starts up, it will start up with the native architecture, even if you told the GUI to run under Rosetta. So what you have to do then is to get the native thing to run under Rosetta, for which there is magic, but I have to tell you the magic. So is anyone here running, obviously, people here are running M1 Macintoshes? Okay, so here, all right, so let me show you what you might have to do. You will have to say, applications, well, whatever this is, PD, whatever, and then contents, and then resources, then bin, then PD. That is the actual PD program. And to run that from the command line in 86 architecture, you say arch minus x86x64, I think. Okay, and I'm going to just double check that. Yeah, I probably didn't get this exactly right. There is a, so what's it going to be? It might be IA64? Probably not. I think there's an underscore in there. How can you find out? No, come on. I did this just 2 days ago because Philippe Mannery is trying to run something in PD on. It's the philosophy art. Oh, come on. No. Did anyone find it? Ah. Oh, arch minus arch x86-64. Maybe, okay, this is it. There is misinformation on the web about this. Maybe it is arch minus arch. That's weird, but x86-64. Try that one and see if that gets PD up and running.
But, sorry, why do you need to change the architecture file?
Because the extern, the
Okay, they are only the
yeah, right. In other words, I have yet to realize that I have to compile. This happens to me every week or so, that some useful thing that I've done doesn't compile under some architecture change in some operating system or other. And this is an example of that I'm only discovering right now. Sorry about this. Okay. So that is now this is how you launch PD in order to be able to run x86 externs within PD. You do not need to do this if you just want to run PD, but if you want to do this until I can manage to figure out how to compile fan for blah, blah, then you have to do this. Now, so what I want to do, okay, so first off, stop me when you have trouble doing any of this stuff, which will happen. The first thing that I think you will want to do is go get the, oh, it changed all my nice fonts. Oh, that's all right. Work, patch, machine learning, fan. So this should be the contents of the file that you are downloading. And where I propose that you start looking is, curve fitting.
Sorry, can you show again the SCP command?
Yes. It's right here, but let me see if I can get on one line. Ah! See if I'll get on one line. There it is.
No, the SCP command to download the SCP command to download.
Oh, that's just a URL. And that is, ooh, where did I put that? Right here.
So small.
Like that.
Okay.
What you're seeing is 1979 era programming style transposed with great difficulty onto the realities of 2023 computing. I simply refuse to join the modern age, and that this has its certain disadvantages. That said, the World Wide Web only came in about 1994, at least where I could see it. So we're really only going back about 29 years in time.
So, I don't have the name of the host.
Of the host, msp.ucsd.edu.
Okay, this is the host.
Yeah.
Okay. Then you should have
Well, yeah, I think what you do is you just take this and copy it right into your browser. And then you get this, right? Sorry, I should have made a simpler URL.
It says that it's not accessible.
What?
Is it working for you?
Not accessible. Oh, no. Oh, sorry. Okay. Okay, that's bad. That's something that I don't understand about HTTPS that I have to learn. Because I'm trying to make everything only HTTPS, but I still get these weird server hoo-has. Okay. Now, okay, so what I'm going to do is try to get those of you who have PD working to be able to run this patch, and then go back and try to get people who don't have PD working to get PD working so that they can run the patch. Are there people who don't have PD itself working here? Probably, yeah? Oh, yeah. Okay. All right, so we will want to spend some time doing that. So let me show you what's up here, and then you can decide whether you want to go any further. Okay, so this is a very simple machine learning example, which I talked about a little bit this morning, which tries to predict the stock market. And so what you do is you try to learn a thing, and the thing itself is the simplest possible, what's the right word, synthetic kind of example, which is, I'll show you quickly and then slowly. You just draw something in here, and then you see if the network can learn it. And so what you do is you follow the instructions, number one. Number two is create a training file. I'll show you that file a little bit later. And then create a nice network, and then train the network on the file. And then it does this for you. Actually, you might not see that because I've got standard error and you don't. And then you can test it, and what the testing does is run numbers from 0 to 99 through this thing. Oh yeah, the x-axis here is 0 to 99, and the y-axis is -1 to 1, as usual. And then I'll run the network for all the inputs that I just trained it on, and then I'll get this, right? Which is my neural net learned version of this function, right? And then what I'll do is, oh gosh, that was horrible, let's give it more hidden layers, right? So I'll create a new network with more layers, and then I'll train it again on the same file. Train on file. Yar, 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 yar. Oh, it's, you know what? Maybe I need to give it more iterations. Let's multiply that by, I don't know, some large number. Let's try it again. Actually, I can hit this repeatedly, I think. Can I? Train on file, yes. Because it will go off from where it was. And this is this error function, and you can see the same thing as before, that this thing is sort of doing as well as it's ever going to be able to do, because you can see that the error is not dropping any further now.
So, just to give an information, I was able to, on my Mac, to open the patch just by ticking use Rosetta on the PD
Really?
application. Yes.
Okay. So somehow PD inherited Rosetta from the GUI program that started it. I don't know how that happened. I'm glad it happened, but I don't, right? And maybe it will never happen again. Okay. And so it's having trouble training it. This is the same sort of thing that we were seeing in David's example. But if I, and I can't get any better than that. So now let's see how well it did by testing it again. And gee, so it thinks that this thing looks about like that, right? Now, yeah, question?
Forgive me if you already covered this. In my console, I'm seeing not initialize.
That is because, I think, because you have to hit one of these create things.
Sorry, because security and private, I have something that like security, it cannot be open because you're not a verified developer.
Yeah. Oh, that's true. You should never run anything that I wrote because it's always dangerous, right? Music might come out of your computer. It's really a bad security problem. And now, so there's a way that you...
Security and privacy make a law anyway.
So there is a command line thing that you can do to unprotect a specific program. This is for pure data, or this must be for the plugin, yeah.
But if you go on the Mac, you go to System, Preferences, and Security and Privacy.
Yeah.
It asks you to allow anyway.
Okay. So it lets you in finally. Okay. There's also a command line way you can do it because sometimes you can't get it to do that. I've never understood all that. Just give it some more. Huh. Okay. Right. Okay. So I don't know if are people still trying to catch up? I think you are, some of you. All right. So I think there's something very interesting to learn here, which is that, let's go back to okay, so first off, let me explain a couple of things about this object. So the thing that you downloaded contained both some test patches and also contains this object called Artificial Neural Network Multi-Level Perceptron, which is the thing that we're using here. It's the active ingredient to this example and to all the other examples in this zip file, right? And so what this thing does is, well, okay, so it does this kind of thing. It takes whatever each layer of this thing makes a linear combination of the inputs and then runs the result through this saturation function, and then that's the output, and that's what one of these objects is. And what the neural net does is makes a topology of these things. And in this particular case, what it builds is a topology where you specify the number of layers, and if there are hidden layers in it, which are layers in the middle between the beginning and the ending part of the thing, you specify how many neurons there will be in that particular layer. So here, where I asked it to make 3 layers with the middle hidden layer having 10 objects, what that did was that made, let's see, I think there's 1 input because there's just 1 input number. There's only 1 output that we're creating. And there is a hidden layer with 10 of these things. right? Like that, okay? And so what that's going to do is, well, I don't really even know why the first thing is there because it's just looking at the input. These things then are going to create a bunch of functions, each of which will look something like this. Hello. Okay, so the input is going to range from, wow. Input's going to range from 0 to 99. Right? And each of these functions here is a linear combination of all of the input followed by a sigmoid function. And so what that can do is that can make you a sigmoid function with a specific onset and a specific sharpness. The onset and this sharpness will be then controlled by the two parameters that are here. There's one that I didn't mention, which is you feed it the input network, and you also feed it a non-neuron, which has the output of always 1. So that if these numbers here are A and B, what you're doing is you're computing AX plus B, and then you're saturating it. And that just means make a sigmoid function and move it to left to right or forward or backward, right? And then what we're going to do is take those things and make some linear combination of them, which then can create things that have steps up and down in various places. This is what a linear combination of these things might look like. And then we're going to clip that, which we'll just shave off the top perhaps. And that's what we're going to see on the output here, right? So what that makes us believe, and here's where you're going to see that I don't know what I'm doing. I'm going to make a function that it likes to find out about, and then I'm going to make a function it hates, right? So even with only 3 intermediate layers, if I give it an easy function, like that, that's the kind of function that you can make out of that network that I just showed you in the other page, right? And so if I now train this simple network on, I wrote this in the wrong place. I'm sorry. This is the test. This is nonsense. Go away. This is the thing I want to do. Sorry. Okay, easy test. Well, that wasn't as good as I wanted. All right, good enough. And now generate test file. I've already created it, but we can create it again if you want. And now I'll train it, and it learns really fast. It did pretty well. The error, this is, by the way, a mean square error, so a true error is the square root of this, which is about 1/50th on a scale of -1 to 1. And now if I test it, test, I get, my function back, right? And now I'll do something that it really doesn't want to do, let's see, which is, well, all right. It's got 3 sigmoids, so it might even be able to do this. It might not. We'll see. I'm trying to make that smoother to be nice to it, right? And now, again, make a trainer file. I'll start again with a new network. Train it. Ooh, it hates it. Now this is what failure looks like. Failure looks like an RMS error of 100, which means a mean error of 1/10, and that when I test it, gives me, it just slapped one of them down and gave up, right? Now this, and again, David knows more about this than I do, so ask him, but there are different optimization algorithms that might be better at finding non-local solutions. So problem here is there are, we're already, this is about a 10 or 15 dimensional space we're searching in, right? Because there are 3 neurons, each one has 2 inputs and 1 gain, maybe, I can't remember, and maybe just 2, I can't remember. I think there are 3 parameters per neuron here, and I think there are 4-ish neurons, so maybe we're talking 12 to 15 parameters total. So we're in a big space, and there probably is something that that's much closer to this than it could find, but it couldn't find it because it doesn't have a really smart algorithm. It's probably doing gradient descent. And gradient descent is great if you have something that points you decently well to the global minimum from wherever you are, and does horribly if you have something that's more jagged and messed up, like what I'm giving it to do here. Now, and again, I'm using a very simple, straightforward default learning method. That's to say, optimization method. And if you had a smarter optimization method, you might be able to do somewhat better, but how much better could you do if you had a problem that was 1,000-dimensional instead of just one-dimensional? Don't know. By one-dimensional, I mean there's one input and one output here, right? Or I could say it's only a 12-dimensional problem because there are only 12-ish parameters in this whole neural net. And it's already failing badly enough that I'm wondering if I'm ever going to spend my time messing with learning algorithms. Except that, actually, you can do cool things with them, as we all see all the time. So this is actually worth pursuing, even though, as I'm showing you, the basic thing that it does is, yeah, I don't know if it even works, right? So let's see this thing that it did a horrible job of optimizing. Let's see if we do better if we give it more neurons to optimize it with. And I'll do this in two ways. One is to just give it more neurons in the middle. I predict it's not going to do any better because it already only really used one to do that. It couldn't figure out that it wanted to use more than one. So let's create a heftier one and train it. Oh, it did much better. And now whoa, pretty good. All right, I was trying to make it hate itself, and I actually did something it liked. Okay. So and last time I tried this, it was just a complete mess. So let's just give it something it really will hate. Okay, create, train. Ooh, it loves that too. Oh wait, I drew wrong one. Sorry, got to mess with the training file. It's cheating to mess with the output file. You're not supposed to do that. Train. Hello. Oh, make. Yeah, thank you. Make trainer file. Then I don't think I have to create it again, but I'll do it anyway. And now it's. Oh yeah, it's going in circles now. And now it's going to be bad again. Yeah. Oh, not as bad as I expected. Right? Now, if you were trying to use this to drive you safely to the supermarket, you'd be dead, right? But on the other hand, using this to control synthesis parameters, nobody dies even if it fails, and probably this is not going to sound as bad as you might think it would. Notice also that, all right, so certain kinds of functions are good for these artificial neural networks, and certain kinds of functions are very bad. But the things that it does well and badly are different from the things that, for instance, polynomial approximation would do well and badly. In particular, there's no problem at all with discontinuities. So here's discontinuity city, right? And it just knows that to make a nice discontinuity, what it has to do is just make those sigmoids real super sharp. So this, I predict, no. All right, the reality is contradicting me. Yeah. Sorry, that wasn't true what I just told you was going to happen. It should be the case that it can do step functions just great, and polynomials obviously are not going to be able to do that ever at all, right? By the way, it's not failing because it's not differentiable. This differentiability thing is in the optimization. It is not in the actual function that it's trying to match. That function can be as discontinuous as you want, right? What it, in higher dimensions, what it seems to like to do, so let's go back here and talk about what a sigmoid looks like. Okay, so here is now a graph of a sigmoid. I'm going to just draw. This is like two dimensions of input, x1 and x2. Except, let's put me in. Don't know why it's doing this to me. Okay. Okay. So imagine a plane. I'm trying to draw it in perspective, and now I'm going to draw what a sigmoid looks like as a three-dimensional plot. It looks something like this. Starts down, goes through 0, right where the line hits it, which I didn't get right, like that, right? So there's like a pseudo three-dimensional representation of this nice sigmoid function as it looks like in a higher dimensionality. And now if you have 3 or 4 of those and are making some nonlinear combination of that, you ought to be able to make things that have roughly planar transitions up in this higher dimensional space, but it can have transitions where one plane hits another plane and bends over and then follows that plane for a while, right? That kind of thing. Now, do you think that the thing that you're trying to train looks like this kind of a function? Can you even visualize what that means up in 500 dimensions? No. But can you come up with some sort of way of thinking pseudo-logically about what kinds of functions you might want to try to approximate with this collection of functions? And if not, why are you using multi-level perceptrons at all? It's just a class of functions. There are many, many classes of functions in the world. This particular one was come up with in the 60s by people who oversimplified what they thought neurons were doing in a way that completely abused both the idea of a neuron and the idea of intelligence. And why on earth are we using this instead of some other class of functions? For instance, spline functions. Well, in fact, these are a kind of a spline function, right? But you could actually like make yourself an optimization thing that fits something with splines. In fact, Jean-Claude Risset optimized a trumpet sound by making line segments and just making line segment functions that mapped the amplitudes of harmonics of a trumpet over time, and did this in the 60s. And you can do this in PD. You don't even need any externs. You can just write a patch for it, and it does decently well in one dimension, right? But then, why in 500 dimensions can't you come up with something that is actually designed for the particular problem space that you're in, as opposed to using multi-level perceptrons? The answer seems to be that people have spent a lot of time optimizing these multi-level perceptrons, and they haven't spent a lot of time optimizing whatever the better class of functions is that you might actually be able to think of as a researcher who has a brain. And so maybe you could throw away all of that work on optimizing and actually really think functionally about what class of functions you want to best approximate the shape that you are trying to learn in your computer, right? And that, by the way, seems to me a completely wide open research area that I don't think anyone is really writing seriously about, because everyone's using MLPs. And I don't know why this is true at all, except just from pure inertia. But 40 years worth of inertia. What's going on here? I don't know. And I would like an answer to that someday. Or I'd like someone to break out of it. And let's see, I'm supposed to talk until 10 minutes from now, so questions. And then we'll get back to something that actually does something useful, because what I'm doing is trying to show you what you're all doing wrong, right? And you really want to know what you can do that's interesting and positive, right?
Do you know of any more biologically plausible neurons made or modeled with PD? Because as you mentioned this morning, the activation is kind of clock, more or less.
Yeah.
Fast, and time is super relevant to the way the neuron works. For example, when you have the coincidence of activation and the firing of a neuron, and the learning process takes place, etc.
Right. For instance, your hearing mechanism, the neurons are actually up to a certain frequency are pulsing in synchronization with the waveform that's coming into your ear. So it isn't which neuron is firing, it's actually the speed at which the thing is firing that matters, right? And I don't know of anyone who's doing this, and in fact, I wouldn't look specifically in PD or in computer music to find this. I would look and see if some of the neurologists are trying to make models of actual brains. And I think I'm seeing people work on very simple kinds of neural structures, like zebra finches and things like that, and getting somewhere with figuring out when a zebra finch ought to chirp, and doing it by making a real model of a proper working neuron. But I think that's just wide open, because it's a much, much harder, it's a much, much harder but more interesting problem, I think, than that of multi-level perceptrons. Yeah, that's an interesting thing to find out about. But I'm pretty sure that the people who are doing that well are not the people in computer music. Yeah. Other questions? Or yeah. I mean, these are all things that people should should write a PhD dissertation on, right? Yeah?
But do you think that Raylu was biologically inspired too, because it has a high clipping feature? You know, it doesn't have any energy at all going into its activation function, and it just puts it at zero.
Yeah. Well, that's true of my stomp box too, right? Because it can't, it goes from 0 to 9 volts. So that's a thing, but that's much, much more widespread than in neurons. But somehow that doesn't correspond exactly to the question you asked, though. But yeah, clipping is universal. And clipping is powerful, by the way. If you, here's another thing. Let's take the first half of this thing and extrapolate it to see if it can recover the second half. Right? Wouldn't that be cool? But that's the stock market extrapolation problem. Well, I actually made this morning. Here's generate a training file on the left half of this training data only, right? I should show you. I'm going to show you the training file here if I can find it. Yeah. So a training curve for this particular package looks like, here's the number of training points, here's the number of inputs, here's the number of outputs, input 0, output minus 0.4, and so on. And that is this curve, except that in this particular instance of it, I generated a file that only goes up halfway. And now we will train our neural net on that. I guess, I should probably reinitialize, just so that it doesn't have any memory of what it did before. And it's training, and it's training, and it's about got as well as it's going to get, and it did. Ha! It predicts that the price of wheat is going to go up and is going to clip at +1. Right? So, good thing about this is that when you're using good thing about this is that when you're using sigmoids to extrapolate. Another point from this morning, everything that you're ever doing is always extrapolating as soon as you get past about 2 dimensions, because you're always outside of the convex hull of the training set, right? But sigmoids are good for this because sigmoids flatten out as they go off to infinity, whereas polynomials, of course, just blow up, right? So even though this has no way of predicting the future, it at least doesn't give you 10 to the 10th for an input value of 100 as it could have otherwise, right, if I was using polynomials. So this is another thing. This is perhaps a reason why multi-level perceptrons weren't such a terrible choice of spline functions to use in these kinds of applications, is that their asymptotic behavior is not exactly well behaved, because it's stupid, it just levels off, but at least doesn't blow up. So it's better to level off than to blow up, I guess. Right? So that's the thing. But there are many other classes of functions that would have that property too that you could think about. All right, it is pushing 4 o'clock. This clock is an hour slow. So I'm going to cede the floor for our next workshop. But maybe there's time for one last question.
I think we have time for questions.
Oh, okay. We'll just make a little time for questions, or diatribes are fine too. Like if someone here is just completely disagreeing with what I'm putting down, then that would be a good thing to find out about. Because then we can have a controversy, and then we can go home and think about stuff. No.
So here you use an external library for that. Would that be possible to develop that purely in PD?
Oh God, maybe, but I think the optimization code is written in C, and I think in PD it would be very slow.
Okay.
So yeah, I wouldn't do it. And in fact, if I were doing this, if I were a lot more serious about what I was doing here, I would reach for, you can embed other programming languages in PD, so I'd be calling one of the vector, TensorFlow, blah, blah, blahs, and doing all my stuff 10 times faster. But as you can see, I have yet to get conceptually past the stage where compute time is even a problem, because I've already got so many conceptual problems just just tracing a one-dimensional function that I can't get any further than that. Yeah. Other questions? Or reactions? Yeah. Okay. This morning's other example is in that package too, the one where you can move around in the Hammond organ space.
Well, thank you, Minner. So we're going to take a break for 30 minutes until 4:30, at which time we will have our final workshop for today with Celeste. So coffee has been served upstairs, tea as well. So take a break, go upstairs, have a good time. We'll be back in 30 minutes. Thank you. Okay, everybody, this is the last session for today. Celeste Betancourt is going to deliver a workshop on the talk that she gave this morning. This will be the last presentation today. So please enjoy. Thank you.
Well, hi again. I'm going to try to well, as David, I have a lot of examples we could try to go around. My plan in general terms is to start with Chalk as a language, because I know there's some people never heard about this language before. So I'm going to start with a very simple example of how to make a sound and a rhythm. And then I'm going to try to jump into the new features of the language. So the first example is going to be like 5 minutes, very, very short and fast, just for the new ones. Then I'm going to jump into the new features of the language, which are the ones that I know no one knows because are just released. And has been released in the last few weeks, months, like operator overloading, which I think is awesome and cool. I'm going to explain a simple example on our new feature collector, which is a very powerful thing to extract MIR features. You just replace something and then you have a lot of information with 15 lines of code. And then my plan after that would be doing the HMM simple example using Markov chains, like from comparing hard coding the rhythm and then using the Markov chain and then showing that it's very easy. Finally, there's more examples I can show. One using the Chagall library. That's not essential, but we can go and touch that. And also there's more examples you can find in the repo. So let me show you. The code is in this webpage. It's my GitHub. The repo is PAW Workshop. And you will find this folder with these files I have here. It's a folder with 6 audio samples and some Chalk code. This is the GitHub. I'm going to show you again. Yeah, don't worry. So it's this one. It's github.com/Celeste Betancourt /PAW and then worship, like that. We're gonna need you to have a very updated version of Chalk, because if you're using an old one, probably some of the features I'm gonna show you will not work. Like operator overload it's in one of the newest versions. That should be, if you install Chalk in the last month, I think it should work. It's probably the last one. But we can have a test. Let's see. Okay, so in this same repo, in the repository, there's some, in the README file right here, down, is the reference for everything. So if you need to install Chalk, the first link that's here will take you to this page. And then that page, you can see this link that says download Chalk. The Mac installer that's on the page, it's 15018. That should be enough. Yeah. We can use the web chuck if, well, that's a very good option. If you don't want to install anything, you can simply go here. So there's another link here that says web chuck. And you hit the second one, and it will take you to this page. That should also work. Yes, that's one of the good things about this. Like we are thinking all this chalk stuff as a very educational tool. So that's why this should work and it shouldn't be a problem. It has chai, it has operator overload, so you don't need to install anything. You just go here and it will work.
Some years ago, there was something called PAW. It was Paw's for the Chuck.
Yeah, it.
Not my name.
No. I think it's Roman's idea, but it's a good thing because we have someone to blame about that, and it's on the room right now. Well, actually, 2 people in this room are to blame about that. It should work. It was working, but then after some updates.
There's a GitHub for it now. It's dedicated for multiplayer, so karma/.
Yeah, but I tried to install today and it wouldn't. Yeah, but for me, Linux today, it didn't work. Yeah, but so it should work. If it doesn't work, blame David Brown. Talk to David Brown. He's in charge of that little thing, which is amazing. I forgot to talk about that in the morning because Chuck is very good for control. So you can have control of what's going to happen, triggers, turn on, turn off, automations, but not good for describing DSPs. It's more complicated than Faust. So it's good to have FOC because that way you can describe your DSP in Faust and just use the object and control it from Chuck, which is a very powerful thing because then you have the best of both worlds. Like have a sequencer that's on Chuck side that triggers Faust synthesizers, and that's freaking awesome. But we need. Well, I think that will not work yet in the WebChuck version because WebChuck doesn't allow you to upload chuggings until last week. We get to compile the WASM file, so probably the next version that's going to be Chuck 1.6 is going to have the FAUC plugin on the web. Yeah. Okay, so is anyone having, like, it shouldn't be any problem. If you want to install Chuck, you could just go install it. If you don't want to do that, just go to this page. Yeah, that's in the README file. And you can just try everything here. Okay, so let's start with something. I'm going to show you just the example. Okay, so I think we're not going to touch this part. This was the example I showed you in video this morning. This mosaic code. It's 2 files. The first file is the mosaic extraction feature. So you just put any .wav file.
Sorry.
Yeah.
So the name is not Chuck, it's
Mini article is the IDE.
Okay. So the application, okay, but when you install it, if you look into your application folder, you won't see Chuck.
You will see mini article.
Yeah.
Yes. Yeah, at least for Yeah. At least for Macs and Windows. Linux will not have mini article, but Chalk, because, well, it's different. But yeah, you will see something called mini article. Yes. So feel free to interrupt me whenever you want. So I'm not going to touch this example, but you're going to have it just if you want to play with those. So this mosaic extract will extract features of any WAP file, any file you want, and it will extract any features you want. I'm going to explain this in a bit, but like right now, as you can see,
What file must be mono or can be stereo?
it could be any, mono or stereo. So I'm just going to go very fast through this example because I'm not going to touch it in the workshop. So this part, we are going to be touching this part, is the feature extraction. So Chalk has a very powerful MB library for doing audio extraction now, and we're going to make it bigger in the next month. In this case, it's extracting the centroid, the spectral flux, RMS, the coefficients of the frequency, and the spectral chroma. So it's extracting those features and then is making a file with those features. And then with the other file that's here, Mosaic Synth microphone, it will play as the video you saw, like G1 making Screamo in the morning. So you just use this one to extract the features, and then you use this one to play with, and you will get something like this. I'm just gonna show the example running, but it's the same code you're gonna have. So I'm gonna turn on my microphone. Hey. Hi. Ooh. Well, this is a file that's doing this, but if you just put any other file, it will make a different mosaic, which is a different synthesizer kind of stuff. So that's just for showing you. You're going to have that code. It's in this repository, but I'm not going to explain it in deepness. It's just there if you want to play with this part. Because this one is more complicated for like in Chalk stuff. And I know some of you have never used Chalk before. So that's why I'm going to start with some basics. So from scratch, we're going to make a very like 2-minute example of how to make Chalk do stuff. First thing, let's create sound. So sine oscillator is the abstraction for that. You just put a name. In my case, it's going to be called Celeste, but it could be anything. And you connect that. This is the Chalk operator, which is very overloaded. It works for everything. In this case, it's like a connector, like a cable to the DAC. The abstraction for the digital analog converter. And then easy, you just type an amount of time. Second to now. That will be the Hello World Chalk program. It's a very simple program that will speed a sinusoidal oscillator for 1 second. So you hit start web Chalk, it will say here web Chalk's ready, then you hit play. My audio is not coming from the, let me see something here. I heard some beep. Yeah, well, that's the hello world. Yeah, great. This is the hello world. So I was explaining to you this morning that this language compared to every other language in the world, like I think this is the most special thing of this language is this kind of sentence, like statement, because it's very specific of the amount of samples you want. Like this program is explicitly saying, give me sample rate at the level you have your setup, your sample rate, it will speed that amount of samples. So 1 second in this computer is 48,000. It's going to speed exactly 48,000 samples, and then it's going to stop. And that's great because what I was saying, it's very useful for controlling stuff. I think everyone's did this fine, so now I'm going to make a variation very fast. I'm going to just add a frequency. This is just a very kindly introduction to the language. And then we just do 880, and I don't know, just copy paste, and then 666. Something like that, and then you hit play again. I was just copy pasting things. You can just put any frequency you want. That frequency is in hertz. Well done. Now you know how to program in Chalk. Everything else in Chalk works almost like every language in the family of C or Java. Almost the same thing, like C++, kind of Java, kind of JavaScript when it was more not functional, but like the older versions. Kind of C, everything works the same. So just a very fast, you can do a while loop, you can do a do repeat, you can do the repeat, you can do a for loop, and everything is like syntactically it's exactly like C++, semicolons. Well, I think you have the idea. So this was the first example, and we know how this works now. So I'm going to jump into more deep stuff because if not, we're going to be stuck in the simple things. I could keep this thing here. What about the analyzers? Because that's what we want to do in this workshop. Everything in Chalk could be connected like this if it's a signal, but then if it's an analyzer, we have another operator. And this operator is this and this. This is the operator for analyzers. So we're going to try to analyze this a simple code. It could be a sinusoidal thing. So what I'm going to do is, instead of doing this connection here, I'm going to connect this to an FFT object. And then I'm going to connect that to any analyzer. So if you go to the page, I was in my repository, you go to the reference. The Chalk reference is pretty well documented since this year. It was awful before, but now we made a great job. Like, we have examples and many other stuff. So we have the unit analyzers here. So you can just pick anything you want. I'm going to just, for the purpose of explanation, just use the centroid. So I'm gonna do the FFT, and then I'm gonna upchuck. This is the operator that's named upchuck, a centroid. I'm gonna call that cen, maybe. And then I can connect this to the black hole, which is like an abstraction again of a duck that doesn't make sound, because we just want to analyze this. We don't want to hear anything. Like this was the old way of doing it, and it was good. But now we have this new thing that will simplify a lot this. It's called feature collector. Am I wrong here? Yeah, that's the name. Oh yeah, I know what's the problem here. Collector. Okay, and let's call this like this. So this new feature will help us with a lot of stuff. So after doing this, you can call this function up chuck. This is the function that's like run. And then we can figure out using this function how many features, the number of dimensions of the extraction we're using, which is important because maybe you don't know how many outputs is going to give you the centroid. Maybe you don't know. So you're going to use this. Everything is on the code I sent you. So we are using this example. If you need to see where are we working, we are in this example that says hmm.ck. That's the one that we are using as reference. Okay, so I'm going to print that number just to see if it's working. This is the print statement in Chuck. It's called the hack operator. And you can run that. Okay, so you see in the console here, I'm pointing there, the amount of the dimensionality of my analysis is 1. That means centroid is just giving you one number, which makes sense if you know what's the centroid. But it could be different because if you're extracting coefficients like MFCCs, you can customize the amount of coefficients you want to extract. It could be 56, for example, and this number will be 56. If you extract other things, there's a lot of things here. So RMS, for example, will give you 1. Chroma will give you 12 dimensions. And each analyzer is going to give you different dimensionality. So this thing is very easy right now because now you have the number. Okay. Now what we're going to do is to finish, like I'm going to go back here to my example. We're going to set the window. So I'm setting the window size for the analysis, the window type, and the size of the FFT. Okay, again, if you need to see where I'm copy-pasting this, it's in the example that you should have in your computer that's called HMM. So far, what are we doing here is, this is the size of the FFT, the bin size. This is the window we're going to use. In this case, it's a Hanning window, same size. And then we define this hop size, which is half of the window in samples. And we are going to store that in a variable of type duration called hop size. Finally, we're very close to finish this example. We need the function to actually extract the feature. So I'm just gonna, again, copy paste that from the code you should have. This is a function definition in Chalk. As you can see, it's pretty similar to any C family language. Function, the return type is void in this case. The name of the function, here you can put the arguments if you want. This is an object-oriented language. This is not a functional language, so it's very different from Faust, but more similar to many of the languages you can see, like for common software. This is a while loop. This is a very different thing that happens only in Chalk. Most of the time, you always need to avoid this kind of thing. You never want a while true in a C++ code unless you are very conscious about what you're doing. But Chalk, this is a very Chalk construction, like a very Chalkian construction, because what we want to do is just keep analyzing this audio as far as we want. So the while true style, it's a very common construct in Chalk. Again, this is the wrong function for the analyzer. Then I'm just going through my dimensions. In this case, this could be, we don't need this. But I'm going to keep it because I'm going to change the analyzer in a bit. So for now, this could be just ignore, and we can use just this value here, and then the hop size. Okay, so now we Spork. Spork is a very Chalkian thing. Chalk is a very special language for controlling stuff. So when you're controlling music, you need polyphony, multi-threading, because every single instrument is going to be running in a different dimension in terms of like triggers. So Spork is a very keyword, a very special keyword in the language to say, I want to run this function in a different, thread of the main one, just because I don't want this function to interrupt the rest of the code. So that's why we use this function that's called Spork tilde. That's Spork and then a tilde. We put the name of the function that we want to Spork, or just put in a different thread. And that's our feature extraction. And then we're going to just run the audio we have here. So the centroid of a sinusoid that's changing frequency. So let's play that. Okay, that's the centroid, that's the centroid, that's the centroid. You see there's 3 values here. The centroid for the 440 hertz of a sinusoid, it's this value. The centroid for the second frequency appears here. And then finally, there's a different centroid here. And that's it. With this code that you can just copy paste anywhere in any Chalk program, you can just switch your analyzer and it will give you whatever you want. So if you want RMS, the only thing you need to change is RMS. Like you change the analyzer and then you run it and it works. So RMS for the whole frequency is the same, which, okay. I'm going to print something to know. I'm just going to update here. Okay, what if we want to flux, a spectral flux? That's the spectral flux of this function. I don't know. This fancy statistical analysis that's called kurtosis should work. Yep. Again, 3 different values. Let's say chroma, spectral chroma, whatever you want to use. It's pretty easy. Okay, that's the spectral chroma of this function. that I'm okay, it's just running and it works. So that's the first part of our workshop. We learned how to do easy things, and now we learn how to analyze any audio. Questions?
The sound wave must be a frequency usually.
It depends. It depends on the analyzer, and that's why I just posted this reference in the help you have, because each one will give you different things. So, for example, Centroid, if you click Centroid, it will give you here some examples. Each example explains what the Centroid should give you. It should be a frequency in this case. But for example, chroma, I don't know what's chroma or what's that for. So chroma features from a magnitude spectrum and gives you a vector of coefficients. Each coefficient, in this case, is the amount of one of the 12 tones in a tempered scale. So it will give you the amount of that note that's finding in the whole spectrum, for example. So the chroma will give you 12 values. Almost, I want to show you this because that will make sense. Let me just print a little bit of this, like just maybe 10 milliseconds. So chroma, for example, is not a frequency. Chroma is just a bunch of coefficients that tell you the amount of the presence of that note in the beep. So this is like C, C sharp, D, D sharp, E, F, F sharp, G, the amount of that note that it's finding. This is not precise, as you know. It depends on the window, it depends on the bins, because we are just analyzing, in this case, 1024, not the whole frequency spectrum as independent bins, but kind of gives you an approach of what's given, like, of the frequency content. So yeah, the reference it's trying to explain a little bit of what the extraction is doing. So this gives you some information of pitch data in the set of frequencies. And I was saying, you can just switch the analyzer with this code. This was very hard to do before, like Chuck 2016. It was more complicated, but now with these some new features, it's pretty easy. You just switch the analyzer, and then you have values, and then you do whatever you want with that. So far, so good? More questions? Okay, so this is pretty powerful. You can just analyze whatever you want. Let me analyze my microphone, for example. Instead of, if you want to analyze your microphone, you change ADC, which is the inverse of the DAC. In this case, is just hit play, and then, oh, sorry, but we need time to run, so let's run this for 2 seconds. Okay, so if you run this for 2 seconds, you should see some values. I think I'm not having values because I'm not connected. My microphone is unplugged. Yeah. My microphone is not plugged. Okay, I'm going to do that again. Not yet. Well, I think it's my microphone, but yours should be working too. I think when I unplugged the example I did before, I just unplugged everything from the mic. But yeah, like you can plug here whatever you want. Like it could be like a sample, for example, like a musical's excerpt or anything. So in that case, you will upload a sound buffer. I'm not going to do this, but I'm just going to show you. So that's a sound buffer, and that will be analyzing any audio you want to analyze. Okay, so let's just keep the sinusoidal thing. Okay, I'm going to keep that for now. So again, we did a very simple program. We learned a little bit how to write chalk. Then we do this feature extraction. This code will work with everything. Actually, I think we're going to make this a class because it will make more sense because now it's the same code multiple times. So we're going to go back to our example code, and that was the first part of this example code that says HMM. We just go from the top to this part. Now I'm going to explain the operation overload because that's one of the new features of the language, which I think is very fun to play with. I'm going to remove this. So operator overload. What's that? Like if you do this in chalk, let's say you want to print what's 2 plus 2, and you run. As expected, you have 4, which makes sense. So this operator, it's just doing what we are expecting this to do, but there are more abstract representations of this kind of operator because what does it mean if we want something like a vector like this plus a vector like this? Like there are possibilities. Like this could be element-wise addition, or it could be just a concatenation. So it's ambiguous. So that's why the language itself doesn't have a description of this kind of operation. But maybe you want to use this kind of stuff for your own cases. Because in my case, when this kind of thing is very useful because I work with melodies. And a melody is a vector of numbers, MIDI numbers. MIDI numbers are just an abstract representation of a note that goes from 0 to 127. Middle C is 60. Middle G is 67. Middle D is 62. So if you want to concatenate one measure plus another measure plus another measure, this makes a lot of sense. And so we need to define this operation because if you hit right now, play, like this makes no sense to the language. You see? Error cannot perform this on object references. But we can define it. And that's one of the cool features, one of the cool new features of chalk. So we need to do this operator overloading, which is almost just a function. So we create a new function. It could be a function. But in this case, we're going to say this is going to return another vector. And then we do this operator word. We're going to overload an operator, and in this case, we're going to overload this one. This is again in the same example. So if you just need to copy paste, you can just go here, go there. So I'm going to overload this on 2 vectors of integers. Let's call P, and it's a vector called P, and it's Q. Okay, so now I need to define what's going to happen with these 2 vectors. So let's say I want to make a concatenation. So what I'm going to do is, there are multiple ways of doing this, but I'm just going to copy paste the code you have in your example, which is this little function here. No, not this one, this one. Okay, so I'm creating a new vector. This is not entirely necessary, but I'm just using it like this so you can understand what I'm doing. This is the vector I'm going to return as part of this operation. And then I'm just going to add all the content in this vector, that's called P, to this vector. And after that, I'm going to add all the content of this vector into the same vector, which is called Q. And then I'm going to return this value. So now if I run it, now it's not an, now in theory we have an object here. You see, this is an object. So the operation is working. And I'm going to try to print that out. So let's create, this is also a new feature. We created this new auto type. Let's call it I. And I'm going to take this out of here. Okay, so I'm going to say this, whatever that is, it's going to go into, this is a new operator. That's going to be used just for object assignment, like erase in this case. And I'm going to, actually it's not necessary. I think we can just do this. Yeah, it should work. This should work. Okay, so now I'm going to print, yeah, we have the values. So what's happening is we are concatenating a melody in this case. So we have a measure. I'm just talking like in abstract, the way I was explaining this morning. So let's say this is measure 1, and it has these 2 notes. This is measure 2, and it has these 2 notes. And when I do this operator now, it's giving me a vector that contains the concatenation of 1 and 2. But the beautiful thing is, like, you just described this for 2 arrays or vectors, but you can do it on 3 or 4 or anything, because this will just go one by one. So let's do another one, like 60 and 62, whatever that is. And you hit play and it works. You see, 10, 1, 2, 8, 60, 62. So this is the kind of stuff that we added to the language because we are dealing a lot with AI. These simple algorithms I show you, more machine learning stuff that AI will say, to be honest. Like to use the more honest word. But we are dealing in a more symbolic layer or dimension. So that's why we are using this kind of operation right now. So far so good. This is a very new construct in Chuck language. This is also very powerful for like creating sequences, as the one I show you in the example in the morning. So this could be like a concatenation of a sequence or a Markov chain of triggers, for example. Okay, so this is like a for each loop. This is a C++ style for each loop. So for everything in this thing, print this thing. We also have the classical for loop if you prefer that one, but this is a new one, so I'm just showing you because I'm showing you the whole new stuff. Okay, so far so good. We can do this with any operator, so you can just create different operators. Like for example, the one I have here as an example. I'm just going to copy paste it. This operator is like the negation operator. So I'm just going to, if you do something like like this, let me do this. Same example, if you have false, and you print false, you have false. So 0 is false. And then if you do this, makes sense because then, oh, sorry, what's here? What did I do? Okay, yeah. So, like, the negation of false is true. It's working. It's 1. But then, if you want to do this on a vector, what does that mean? It makes no sense as a definition, but it makes a lot of sense if you're doing triggers, for example, because you're not dealing with actual vector math or linear algebra. What you do is using this type of construct to store data. So in this case, this doesn't make sense, but with this definition here, what's going to happen is, let me show you. If I just put here this, and then I print. Okay, I need to. Okay, so let's see so let's compare the original vector with the new vector that was operated. So we have 1, 0, 1, 0, 1, 0, 1, 1, and the negation of that one is something that makes sense because it's like negating every element wise. So it's like 0, 1, 0, 1, 0, 1, 0, 0. And again, this is very useful when we are dealing with more abstract or more symbolic representation of music, because music behaves in this way. It's not linear algebra, it's a different type of thing that in this case works as a vector, but is not actually a vector in the sense of the mathematical sense of a vector. So we're not dealing with this as a thing that has to be closed on addition and multiplication as an algebraic group. We don't care. This is just a collection of triggers that we are using for triggering samples. So in this case, this operator makes sense. So this is the second part of the workshop. Now we know how to overload operators. It's a very new, cool stuff and cool feature in the new chalk. So again, I'm going to stop here and questions. Good so far? Okay, so let's continue with the example. So we already made the feature extraction. We already did the operator overloading. Now I'm going to jump this part, but you have it there. This will not work on web chalk because this is a chugging. It's going to be there like in a month, but not yet. So this is the new Chuggle, which is OpenGL inside Chalk. And just to be very fast with this, this is a new, this paradigm, like we're switching the whole thing. The graphics are dependent of the audio, contrary to every other language that deals with graphics. Most of the time, the graphics are running, and you sacrifice samples because of the graphic part. But here, we're trying to guarantee that every sample that you calculate is going to be out of the DAC.
Is Chuggle already in the chat, or must be downloaded separately from the...
Yes, if you go to the GitHub,
Oh, Spencer, no?
yeah, that's there. I show you this GitHub. Okay, so here's the link for the Chuggle. It's a chugging, so it needs to be needs to be installed. Here are the installation instructions. It's not very hard to install. If you have a Mac or a Windows, let's say you just go to the latest one, and there's the Windows. You just copy paste this into the chugging folder, and it will work. Same for Mac. You just copy paste this into the chugging folder. That should be in preferences mini article, and then they will show you where's that. And for Linux, you should know how to compile from the GitHub repo. So there's no binary. You just go to GitHub and compile. Okay, so this is going to be fast. You have the example there, and also you have these two other classes here. This one that's called shader tools, and this one that's called shader type. I'm showing you that just because you're going to keep this code, and maybe you want to keep playing with this. So let me show you something pretty quickly. So I'm just going to comment this part here and see if this works. Looks like I deleted something from here. Okay, so this is just for a reference. This is 138. Where it is? Okay, this part.
What is the chugging folder?
It depends on your computer, but if you go to mini article preferences, one of the windows will say chuggings. You click there and you will see there's a path. You just copy paste everything in that path and it should work. In case anyone or someone wants to see how that works, I'm showing you like this very fast. What's wrong? I think I did. Let me do a chug improve. Okay, so in case someone wants to run that, you need to run in this order these files. The first one you need to run is this one. It's just a definition of a type. So you run this, you load this one in the mini article and you run it. Then you go to shader tools, you run it. Finally, you run the chuck GL code you want to run. This is just some helper functions for doing shaders. You can see this is just OpenGL code. So this is just helper tools. But yeah, I'm not going to stick here because then we're not going to see the HMM, which is the final stage of our presentation. So this code is going to stay there for your reference. If you need help with this, I can help you run the Chuggle, which is very nice because you can have pretty precise graphic designs because Chuck is very good for that. Contrary to OpenGL, which is very complicated to make loops and all the stuff. So I'm just going to leave that there. We're not going to talk about that. We're going to jump into the final stage here, which are the Markov models, the Markov chains, which is the last part of the example you have. Okay, so there's a lot of code here, and I'm going to try to go fast through it because it's a lot, but I think you can catch the idea. So let me just, okay, so the first thing in here where they say chai, mix it with some chocolate. The first thing here is just a synchronization time, so you can have like triggers at the same time. This is the BPM, 130 BPMs per second. This is the, we'll say the note, or the subdivision. In this case, is subdividing each beat by 2. So that's mean like 8 notes, or so quarter notes. These are quarter notes. These are 8 notes. If you subdivide more, you have 16 notes, etc. This is the way you upload samples, audio samples. So I already say this. This is a sound buffer. You give a name, then you connect this to the DAC. I'm uploading 6 different audio samples here. This is for setting the gain of one of them that's very noisy. This one. This is the way to change the gain of the whole program. It was just because when I was doing the presentation this morning, Roman said that it could blow up, so I just put it like this. This is the way you give the path where the sample is. So everything is in a folder called samples, you see. Samples, and this is the name of the audio sample. This is the chalk construction for saying in this directory, in the same directory where this file is, and then read that file. So it's doing that 6 times. This line here is just because when you read the sample, Chalk just want to play it when you run time. So this line is just saying, go to the end of the, like put the playhead at the end of the sample. So it will not play because it's going to be at the end. Okay, so now the interesting part. We are going to create some HMMs. HMM stands for Hidden Markov Model, which is a very simple stuff. It's just you feed a sequence into this Hidden Markov model. You set some weights, like, and you set some initial conditions. You set some emission conditions, and then you have infinite amount of different sequences that are related to the specifications you gave to the model. So I'm creating 4 of those. I'm creating 4 vectors of size 8. Because if you remember the example I showed you this morning, it was an array of 6 by 8, like the sequencer. I created 4 because I'm creating just 4 HMMs, and then 2 of the instruments are hard-coded, like here. So this instrument is going to play the same rhythm every time. This instrument is going to play the same rhythm every time. In these 4 other instruments are going to play the Markov chains that are going to be creating new rhythms every time, depending on what you put as initial conditions. Okay, so this is my initial sequence, is the sequence I'm training my model. If you remember, I was talking about tiny models or small models or small mindsets. This is what I mean. The data here is just 18 numbers. So the sequence is a sequence of 16 numbers, pretty short, pretty manageable, and it's related to the way the kick drum or the bass drum in techno will sound, like boom, 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 boom. So this sequence, it's a pretty easy, predefined sequence of triggers in many of the electronic dance music. So I'm going to train this model using this sequence. Then I'm going to train another model using the same sequence but inverted. And I explained that in my morning talk. What happens with the hi-hat in the techno or electronic music, if you hit a kick, then you have a hi-hat in the other, in the beat, upbeat beat, like that. So you have boom, spoonch, 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 boom, 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 spoonch, spoonch. So that's why I created this operator, in this case. This is a sequence, a different sequence for another hi-hat. It could be anything, it could be any long. So these Markov models will just work with any sequence you gave. The more information, the more precise. So if you, right now it's 16, but if you just copy paste this like 20 times, the model is just going to give you the same sequence every time, because it's just going to understand that you want the same sequence multiple times. But with less information, it's less precise, but that's what I want, because I want this thing to have variety, to sound different, because I'm using it as a generative kind of, like a generator of rhythms. So this also is hard-coded. It's just a vector of triggers. If you want to know what are these numbers and what else can you do with a Markov hidden model, you can just go here, AI tools, you go to HMM, and then you see that HMM has these 3 functions. You can generate something using the length of the sequence you want to generate, and this is the output vector you want to copy the output. You can load a model using the initial conditions, the transition matrix, and the emission matrix. This is more precise. This is just saying to the model, I want this sequence of things to happen with these weights. I want to start with this specific sequence. I want to go to this sequence. And then there's a function that's called train. That gives you the amount of states you want, the number of emissions you want of the model, and the observations you want to train the model in. So finally, this is very easy. And I was saying this is it's a very will not say AI stuff, it's a Markov chain that it's pretty simple to understand conceptually. And finally, I'm about to finish. So finally, we just go and put everything into a player. This player is just a while through loop, and then a for loop that's going through the vector. If the vector is a number 1, it will play the buffer for this amount of time. If the if the trigger array has a 0, it will just let pass time. That means plays if it has a 1, don't play if it has a 0. That's the only thing it sets here. I created 2 functions of those because this one is for the ones that are using Markov chains. This is the one for the ones that are not using Markov chains. And we already saw this. This is just multi-threading. So we are putting this 6 function in synchronization, one on top of the other. Each one is running at this time with this instrument. And finally, we just have a while through loop to just let pass time. And you already saw this example in the morning. This was the example I showed you in the morning. If you just want to run it, you can just need to close right now. Right now. Okay, so I'm going to close now, but you already saw this example. If you want to run it, you need to upload your samples to WebChuck. I'm just going to show quickly that, and then I'm going to finish because Roman is already here standing. Okay, so if you want to run this in WebChuck, you need to upload your files here, and you can upload your web files here. And then you just copy paste the part of the Markov models that's here down, this part. And it will give you the same result I show you in the morning. It's this sequencer that's triggering new rhythms every time using this Markov chain as a source, which is great for live coding because that means you just need to type one sequence, like I want reggae, you give reggae, like the main reggae sequence, and then it will give you a lot of variations just based on the information you provide, the weights of the Markov hidden model. And that's it. Just to finish, there's another example that uses Wikinator. If you want to see, Wikinator is a very popular tool. I already saw that. So you can just go here and check it. And there's another example here that uses Wikinator plus an FM synthesizer plus your mouse, which is almost the same example that Miller was explaining us. This is the training set. You see, there's just one array, one result, one array, input, output, input, output, input, output, and then this thing with a multi-layer perceptron is just going to give us a very sketchy but good enough interpolation between those values. And I think that covers all the things you have there, and you know where to contact me, you know where I live, most of you know where I work, so thank you.
Thank you, Celeste. So just to wrap this up, if you have questions for Celeste, you can maybe ask her the questions here, like while we pack things up, because we really need to leave soon, like because of security. Before you guys leave, there are a couple of things that I want to say. So first, I just want to thank all the people who helped putting this event together, especially Agathe, who really helped us with this, and Stefan and the whole Emerald team, like Sadia, who's already gone, but and Irene, who were, like at the reception, and like a lot of people were involved in the process, and without them, this would not have been possible. Thank you. So when you leave, there's instructions to leave this building. So the main entrance is already closed, okay? So to leave, you have to go in the lobby, and then there's two automatic sliding doors. To open those doors, you need to press a button which is on the wall that says up.